Hey guys, hello everyone and welcome to the channel. Now in this particular video we are going to solve questions from inorganic chemistry part which were asked in your CSIR-NET exam of December 2019, and I'll be taking the exam that held on 15th of December. That means the all India level exam, the all India exam except the Assam and Meghalaya region exam, and I'll be taking two marker questions in this video, right? Because in the last video where I have discussed about the physical chemistry solution, um, you guys requested me to solve inorganic questions as well, so that's why I have made this video. Right now, if you have not watched that physical chemistry video, then I will suggest you to watch this video completely. At the end you will get as a card over there, and you can just click on that to watch the solutions of physical chemistry part as well. All right, so let's start with it. So the first question over here was based upon a very simple concept. It says that the ion having the highest bond order is, okay, so the ion which has the highest bond order. So the basic trick which we generally apply for calculating the bond order is by calculating the total valence electrons. So if you know the total valence electrons, you can easily tell the bond order, right? So if you start it from 14, so if the total valence electron for diatomic molecule, or for the molecules basically, if the total valence electron is 14, your bond order, okay, if I write down the bond order over here, so the bond order remains 3 over here, okay. So for 14 the bond order remains 3. For 13 your bond order decreases by zero point 0.5 value, so it will become 2.5. For 12 it becomes 2.0. For 11 it becomes 1.5. For 10 it becomes 1.0, and so on, okay. Similarly for 14 it is 3. For 15 it will again decrease by 0.5, so it will become 2.5. For 16 a total valence electron, it is going to become 2.0. Then again for 17 it is going to become 1.5, and so on, okay. For 18 it is going to become 1.0, so it goes like that. So by calculating the total number of valence electron, you can easily predict the bond order. Now looking upon the options, if I talk about the first one, which is NO plus, so total number of electrons, you are going to get 7 electrons from nitrogen, and you are going to get 8 electrons for oxygen, and plus 1 charge is there, right? So 7 plus 8 and minus 1 for that positive charge. So overall you will get 14, right? So 14 means the bond order for this particular one should be 3. Okay, so for 14 the bond order becomes 3. All right, so obviously this 3 is the highest bond order which you can expect from the molecules, but yet let's check the other one as well. For O2 plus, if you see over here, for each oxygen 8 electrons, so 8 plus 8 and minus 1 because of this positive charge, so you are going to get 15, and again the bond order for this is going to become 2.5. okay, so this is going to be the bond order here. The third part, if you see nitrogen, so N2, so 7 plus 7 for both the nitrogens, and minus 1 because of this positive charge, so again it's going to be 13, and for 13 the bond order will again become 2.5, so it is again having a lower bond order. And the last one, that is C2 plus, so for each carbon you will be having 6 electrons each, right? So 6 and minus 1 because of this plus charge, so you will have 11 means you have a bond order of 1.5. so that means what it means, that the highest bond order for this particular question which was asked is 3, and that remains in your NO plus molecule. So the correct answer becomes your option number. Alright, so it's very simple, very easy question. Let's go to the next one. Particular question, it says that the expected number of carbonyl bands in the IR spectra of facial complex, this is molybdenum pph3 whole thrice, CO whole thrice, and you have trans molybdenum pph3 whole twice, CO whole 4. So first of all you need to know about like how you can assign these carbonyl bands using the structure, okay. So if you go with the trivial way to find out the types of CO, then you will end up doing this question wrong, okay. You have to understand the application of group theory to understand or to find out the IR spectrum bands, or to find out the carbonyl bands, okay. So this is actually a very direct question. If you have practiced based upon how you can assign different IR bands or different carbonyl frequencies for different types of like metal complexes, you could have done this question very easily. So I'll just give you this in very brief, in very like in a very simple way, in a very precise way. So I'll not be going in much detail. So let's first of all draw the complex. So the complex will actually looks like something like this. Alright, so this is how both the complexes will look like. This is your facial complex, and this is your that trans complex which is given to you. Now ideally, if you look upon, you will find out that these all carbonyls are actually they look like equivalent, so they should give just one peak. Okay, and many people did it like that only, and they thought that the first molecule is going to give you just one peak. But this question will not be done like that. You have to see the point group in this particular molecule. So since we have a C3 group over here, and you have sigma V planes, you know the point group for facial complexes, right? It's C3V. And for this particular molecule, if you look like, it will be your D4H. Okay, so that is going to be the point group of this. Now there is a very basic rule to find out the number of IR bands, or to find out the IR bands. Basically, you can just relate the IR bands like that. It says that lower the symmetry elements, or the lower the symmetry, higher or more is the number of, higher the number of IR bands. Okay, so or your carbonyl frequencies, if you are talking about carbonyls over here, to be very precise. So if you have lower symmetry, more number of IR bands will be there. If you increase the symmetry, your number of bands are going to decrease. For example, it's a very simple molecule. If you take a metal octahedral complex MCO whole 6, this is just going to give you one peak, because it's a very high symmetry element over here. The symmetry group, or the point group over here, is octahedral, so it's a very high symmetry group which is over here, and that's why you will just get one peak. If you lower down that symmetry group, and if you just make it as MCO 6 sorry, MCO 5L, if I make it like that, so it is going to give you now two peaks, where now the symmetry group has been changed and it has become C4V. Okay, so if you decrease the symmetry groups, or if you decrease the symmetry, that means the number of IR bands are going to increase. So in the same way, you can understand from here that in this particular case, your symmetry group is quite less. Okay, and that's why the number of bands should be more over here. So over here, what happens, that these equatorial carbonyls, they are going to give you a same band, whereas this axial carbonyl is going to give you a different band. So the total number of bands are 2, and actually for C3V, we calculated along with this, like if you have some so for C3V, we calculated using this particular formula, that is n minus 1. Okay, so with this n minus 1, you can calculate the number of bands over here. So the number of bands for this particular case is going to be 2 bands. Okay, or 2 peaks. So 2 peaks you will get for this case, whereas for this, all these CO groups are going to be equivalent to each other, because it is a higher symmetry element, and also it has, like, all the carbonyls will be equivalent to each other if you rotate it along C4 axis. So you are just going to get one peak in this particular case. So it was pretty simple to understand this, but for this, it's you have to remember this, that all facial isomers, they give you two peaks, and it is because of the lower symmetry element. Okay, because of C3V. And if you go for the meridional isomers, okay, fine, so that I'm giving to you guys to find it out. Okay, so try to draw the meridional isomer and try to find out that how many peaks you are going to get for a meridional isomer of the same complex. Okay, so that is for you guys. You guys have to do it and tell me in the comment sections below. So the correct answer for this question was your option number 3. Alright, so let's go to the next question then. Alright, talking about this particular question, now it says that correct order of molar extinction coefficient values of the visible absorption spectra, or visible absorption bands for the following species is. Now you are given with 4 different types of complexes, and it is asked that what is the order of molar extinction coefficient. Now a few things which you need to understand over here is that your molar extinction coefficient, okay, molar extinction coefficient is actually going to be proportional to your molar absorptivity. Okay, if you know molar absorptivity, you can easily tell the molar extinction coefficient from the formula, right? And this molar absorptivity is actually going to be proportional to your intensity of the band. Okay, that how intense the band is, intensity of absorption. Okay, intensity of absorption band. Now In order to understand that on the basis of your transition metal complexes, it is very simple to understand that how intense a particular band will be based upon the selection rules, right? So if the molecule follows the selection rule, so in that particular case you can tell that the band will be intense or weak. So I will just give you quickly a order to identify this. So the first one is there are two rules, right? There is a spin allowed rule or a spin rule, and there is a Laporte rule. So both of the rule has to be followed. So the spin rule says that the delta spin, that means the spin during the transition, should not change, and there should be change in the parity. That is called as the Laporte rule, right? So if something is spin allowed as well as Laporte allowed both, in that case its intensity will be highest. Then if you have spin allowed, okay, spin allowed, but your Laporte does not allowed, okay, so it's not equal to plus minus 1. In that particular case also you have two types of cases. First is a non-centrosymmetric molecule, okay, non-centrosymmetric molecule. So those which do not have symmetry in them, they will give more intense band compared to those which are centrosymmetric. So here again the formula, like the rule is same, that is spin allowed but Laporte not allowed, but here it is centrosymmetric, okay, this is centrosymmetric molecule, okay. And the least intense is the one which does not follow even the spin rule, neither the Laporte rule. That means delta S is not equal to 0 and delta L is not equal to plus minus 1. Now let's quickly take some examples for them. So for this, where spin is also allowed, Laporte is also allowed, these are generally your pi to pi star transitions, or you can say that your charge transfer spectra, okay. So all types of charge transfer, whether it is LMCT, MLCT, a ligand to ligand charge transfer, intravalence charge transfer, all of them are charge transfer spectra, and all of them are more intense, okay. That's why you get very intense color or very intense band in the charge transfer spectra. Non-centrosymmetric means the structures which does not have a center of symmetry. Example of them is a tetrahedral structure. Centrosymmetric means those which have a center of symmetry in them. For example, complete octahedral species. For example, if metal and there are six ligand of the same type attached to this, and here if this is the metal and there is four types of ligand attached to that, okay. And the last one is where your spin allowed and the transition is neither spin allowed neither Laporte allowed. These are generally your D5 transitions or D10 transitions, where if you cannot do the transition, right, the higher orbital is already filled. So these are some of the examples which I have given. There are many others which can be discussed, but for the current scenario you need to know this, okay. So this is the order of intensity of band. Now based upon that, if you understand the intensity, you can easily predict the molar extinction coefficient. So we are just going to predict the intensity. Now in the molecule, if you look upon the options given, so there is a charge transfer which you know is going to happen in chlorophyll. So chlorophyll is going to give you the highest intense band, okay. So chlorophyll, okay, chlorophyll is going to give you most intense band. Then in the other, there is no charge transfer spectra happening, like neither in NiCl4, neither in CrH2O6, neither in MnH2O6. So what you have to look upon is whether the molecule is centrosymmetric or not. So NiCl4 2 minus is going to be a D8 transition, D8 molecule over here, and this chromium over here is going to be a D7 molecule, right, and this is going to be a D5 molecule. Now if you look upon them, so yeah, so non-centrosymmetric, so this transition in NiCl4 is going to be where the spin is not going to change. It's going to be spin allowed transition, but there is like it's not Laporte allowed, right, because it's a DD transition which is going to happen over here in the tetrahedral species, and it's a non-centrosymmetric molecule. So that's why the next molecule will be NiCl4 and 2 minus. All right. The next one will be D7, where there is again spin allowed transition. You can have a spin allowed transition in D7 as well, right? If I just show you, so 1, 2, 3, 4, 5, high spin D7. So 5, 6, and 7. So you can have a spin allowed transition because the spin is not going to change. It is easily going to transit, but it's a centrosymmetric molecule, so that's why it will be less intense. So the other one will be CrH2O whole 6 and 2 plus. Alright, and the least one is going to be the D5 species, where the transition is neither spin allowed neither it is Laporte allowed, because if you see the D5 structure, D5 octahedral species, so it is going to be like this. So you cannot have a like same spin transition, because over there already orbitals are filled, and if you want to do the transition you have to change the spin, which we don't have to do because it's not following the spin rule. So the least intense will be your Mn H2O6 2 plus. So that in that particular case you can say that your answer is option number 2. So it was pretty simple. You just have to look upon the intensity order of the absorption. Based upon that you can tell the molar absorptivity, and molar absorptivity and molar extinction coefficient both are directly proportional to each other with that particular formula, A is equals to epsilon Cl. So you can tell that answer option number 2 is going to be the correct answer for that. Alright, let's go to the next question then. This was actually asked from direct reaction of your main group elements, and to answer this question you don't have to apply any concept and all. It's just based upon whatever you have studied. If you remember that, you could have answered this question very easily. Okay, it says that consider the 4 species A, B, C, and one more species is there, D, and it is said that when A and B reacts in the presence of potassium iodide and in the acidic medium, you are getting C. And when you do oxidation of A with C, that means if A and C get oxidized in the acidic medium, it gives you some compound D. So they're asking what is A, B, C, and D. So this is actually based upon the redox titration of iodine with your S2O3. Okay, so you might have studied this, I guess. But yeah, see actually how does the reaction happen. So it based upon standardization condition. So we standardize first of all our thiosulfate on the basis, like we standardize the thiosulfate with KiO3. Okay, so based upon that we are going to do. So since KiO3 is there in all the options, so you can just predict that okay, it's a reaction of KiO3. So let's try to analyze the reaction. So what actually happens that you take KiO3 and you treat it with potassium iodide in the presence of your HCl. Okay, so this is going to give you iodine, and then you are also going to get KCl. Okay, so KCl, potassium chloride, and also you are going to get water as a byproduct. Now this iodine which you get in this particular step, this is called as a standardization condition. Okay, as standardization process, or standardization using potassium KiO3. Okay, now if you have standardized it, you have formed iodine. Now this iodine is actually going to react with Na2 S2O3. That means basically you can call it as S2O3 2 minus, and when you react with, so you are going to get sodium iodide, and with that you will get Na2 S4. Okay, S4O6, or you can say S4O6 2 minus. Okay, so basically if you look upon the reaction over here, so they have already given Ki and H plus. So these two things, Ki and H plus, is already given to you. So that means your KiO3 is somewhere over here. Okay, A and B, among A and B something is your KiO3. Then the second thing, and the product which you are getting is C. So your product is C, that is iodine. So this is going to be your C, this is going to be your B, and when you are reacting this C with some compound A, what is going to be A? So this is going to be your C, right? C reacting with some compound A, or this is going to be your A. So when C reacts with A, you are going to get D. So this is going to be your D. Okay, now you got all the things. So that means A over here will be present, but it has nothing to do with the reaction. Since you are standardizing it, so that's why it has to be there in the reaction. That's why it is kept. Okay, so this S2O3 2 minus will be there in the reaction. So this is how the reaction is actually. So your A comes out to be S2O3, B comes out to be KiO3, C comes out to be iodine, and your D comes out to be S4O6 2 minus. So it was a direct reaction asked from your books. So option number 3 is going to be the correct answer for this. Alright, now let's go to the next question then. Alright, let's talk about this particular question. It says that the common hapticity observed for coordination of C60 to a metal center is. Now, to answer this particular question, it was pretty direct. Okay, if you have studied about C60, that is Buckminster fullerene, you could have easily answered this. But if you don't know, I am going to explain you a little bit. So, in the Buckminster fullerene, if you look upon the structure, so it looks somewhat like this. Okay, if you draw the aromatic structure of this, so it looks quite equivalent to this. Now if you want to look upon a certain fraction of it, let me just show you a particular fraction, and with the help of that we will try to understand this. So I guess you guys have already studied about this kind of molecule when you are preparing for NMR. Okay, we call it as peripheral aromaticity, or in the organic chemistry also, where you have studied about the peripheral aromaticity. And there you might have seen, okay, if you have a certain molecule like this, okay, if you have certain molecule like this, in that particular case what happens, that the aromaticity of side like ring is going to constitute like that is enough for the aromaticity of the molecule. The central double bond, or this particular double bond, is not taking part in the aromaticity. So this kind of effect is called as peripheral aromaticity. I guess many of you know about it. If you don't know about it, I will make a separate video on that. It's based upon general organic chemistry, and it's a very well known and very famous concept. So these particular carbon, these two carbons which are not involved in the aromaticity, they have this particular double bond which can be given to the metal in order to form the complex, right? So just the way we have a complex like this, let's say if you talk about any xantyl ion, you have a complex like this. So here you have a ethene molecule, so it's giving electron, the pi electrons of this carbon carbon double bond. So in the same way, this particular species is going to give this the electron, this pi electron of this carbon carbon double bond. So this is going to be called as eta 2, or the hapticity will be 2, because the electrons between these two carbon is going to be shared. In the same way, if you look upon this Buckminster fullerene, there is a part of it which will be available over here in the molecule. You can see that this particular part will be available for making the hapticity. Okay, so in the complete molecule there will be like you will get many of this kind of part. Okay, you just need to look upon this part. Okay, I'll just erase the rest of the part. So this much part you just need. So in this kind of part, only these particular two carbons are going to constitute this like carbon carbon double bond, and this is going to be shared to the metal in order to make bond, or that's why the hapticity becomes 2. Now for all of these fragments, whatever number of fragments you have in the complete Buckminster fullerene structure, everywhere in all of these fragments, like two of them will be given. So you don't have to add all of them. Okay, overall how many carbons, or uh, how many pi bonds between the carbons are going to be shared? So there are just two carbons, between them one pi electron is going, like one pi electron cloud is being shared to the metal. So that's why the hapticity becomes 2 over here. Okay, so the pi electrons between the two carbons are only being available for sharing with the metal. So the hapticity becomes 2. So there is direct solution or direct answer of this in many books. Okay, if you have read about books, if you have prepared well, you might know the answer like you might know the answer as it is. But this is how you can explain, or how you can understand this, that how hapticity becomes 2 for C60 metal center, right? C60 to the metal center. Now let's go to the next question then. Alright, the next question over here says, for an octahedral copper plus 2 complex depicting axial EPR spectrum, where it is given that your G parallel is greater than G perpendicular, the geometry of copper plus 2 and the orbital containing the unpaired electrons are. Now see, if you have watched my classes, if you have watched my videos on YouTube, there are many videos on inorganic chemistry which are already available on the channel. I will recommend you to watch them very carefully, because many questions, if you see, they were directly taken from there. Okay, so that this was one of that question which was directly taken from my video. And if you know that, if you know the concept, if you have watched my video, you could have done this question very easily. So what it says, that G parallel is greater than G perpendicular. What does that mean? It means that electron density along Z axis, okay, is more, okay, is more than electron density along xy axis. That's what it means. If G parallel is more than G perpendicular, it means what? It means that in copper plus 2, which is a D9 species, you will have more electrons filled along the Z axis than along the xy axis. So if you see this copper plus 2 complex which shows John-Taylor distortion, so you can say that you will be filling the electrons like this. Okay, so electrons are going to be filled like this. So this is how you are going to fill electron, and more electron has to be in z axis. So that means dz square will be lower in energy and dx square y square will be higher energy. So more electron along the z axis. This will be dxz, dyz, and this is going to be dxy. So this is how your d orbital is going to split for this. Okay, so this is d orbital and this is how it is going to split out in the case of your copper plus 2 showing the John-Taylor distortion. Now the condition is fulfilled that electron density is more along the z-axis. So what kind of structure it is? Is it elongated or compressed? Now you know this, right? If you have studied the concept, you know that when the elongation of the z-axis appears, when there is elongation in the z or the axial bond, so what happens? That the energy along that particular axial direction, the energy of that particular orbital along the axial direction decreases. So the orbital along the axial position is dz square, energy of that is lower. So this is like this particular splitting of d orbital is for tetragonally elongated structure, right? And the unpaired electron is going to be in what? So the unpaired electron is there in dx square y square. So the correct answer is option number 1, tetragonally elongated, and the unpaired electron is in dx square y square orbital. So this is how this has to be answered. Let's go to the next question then. Particular question which was actually asked from your nuclear chemistry, and it says identify the following the product of k electron capture by the nucleus. What does that mean? K electron capture. K electron capture means nothing but what happens actually that in certain nucleus the proton of the nucleus actually it absorbs or it captures the electron from the k or l level. Okay, you know that there are different orbits like k shell, electron shell, l electron shell. So what happens that in an electrically neutral atom, the inner atomic electrons from the k or l shell are being absorbed by the nucleus, and this process is called as your k electron capture. So what actually happens that your proton over here is going to absorb that electron from the k shell. Okay, so it can be from k shell or it can be also from l shell. Okay, so for l shell it will be called as l electron capture. So both the processes are same, it just depends upon from which shell the electron is being absorbed. So it can be either k shell or l shell, it depends. Okay, so either it is a k electron capture or l electron capture. In both the cases proton is going to absorb that electron and it is going to form a neutron, and along with that you will get a neutrino. Okay, you will get a neutrino which is going to get formed. So a proton is going to get converted into neutron, and simultaneously emission of an electron neutrino is going to happen. Okay, so the answer will be formation of your neutron, and also a neutrino is going to get eliminated in this particular reaction. So I'll just write down. So what is happening that a proton is absorbing electron from the k shell or l shell, and it is forming neutron, and what is being eliminated is electron neutrino. Okay, neutrino. So that is being eliminated. So answer will be option number 2, which says A and B both. Alright, so this is how this question has to be done. Now let's go to the next question. Alright, so let's talk about this particular question over here. It says that the most stable vanadium species in the aqueous medium is. Now to answer this particular question, you need to know quite a few things. First of all, that what is the most stable oxidation state of your vanadium. Okay, so the most stable oxidation state of vanadium is actually +4. Okay, so +4 is the most stable oxidation state of vanadium. Now over here in +4 oxidation state, it can like you can easily eliminate few of the examples if you look upon it. So in the first example of in the first option, your vanadium is in +3 state. Okay, the oxidation state is +3. In the second option it's in +4. In the third option it's in +3, right? Again, because oxygen will give you -2 and +1, so overall +3. And in the last one again it's in +4 oxidation state, -2 from here and +2 from here, so overall +4. So you can easily eliminate option number 1 and option number 3. So you are now left out with option 2 and 4. Now the second thing which you should know is that the most stable oxidation state of vanadium is +4. First thing. Second thing is that the most stable form of vanadium is the oxo-vanadium form. Okay, so the most stable form of vanadium is oxo, like it will be oxo vanadium ion. Okay, oxo vanadium 4 ion, or it is also called as vanadil. Okay, so that is also called as uh, vanadil. So the most stable form will be oxovanadium ion in the +4 oxidation state. That means vanadium with oxygen. So if you look upon the option, like you are left out with option 2 and 4. There is just option number 2 which has oxygen and vanadium and oxygen. That means you have oxovanadium form in this. Okay, so the correct answer is going to be your option number second. So that's how you have to answer this question. All right, now let's go to the next question then. Alright, let's talk about this particular question over here. It says for a complex shown below in non-fluxional state, the expected 31p and decoupled proton NMR resonance. Okay, so this is phosphorus hydrogen decoupled NMR resonance, and it is given that the I value of phosphorus is 1 by 2. So if you look upon the structure over here, how many types of phosphorus do we have? So first thing is to find out the number of phosphorus. Okay, so you have two types of phosphorus because this is one of the phosphorus which is on the equatorial position, and cis to it you have COPH group, whereas this is second type of phosphorus. Cis to it is your carbonyl group. Okay, so you don't have, and this COPH group is trans to it. So both of them are different types of phosphorus. So this is phosphorus A and this is going to be phosphorus B. Now the in the EPR spectrum, sorry, in the NMR spectrum, if you see, so how many splitting is going to happen? So since you have one of this type, so 2Ni 2Nia plus 1. Ia means the I value of the A type of atom, and this is going to be 2 into, because you just have one phosphorus of that type, and I value is half and plus 1. So you are going to get how much? You are going to get 2. That means you are going to get doublet because of that. Similarly, for second one also, you will get 2Nib and plus 1. If you put the values, so 2 into 1 into half and plus 1. So if you just cancel out, so you will get again 2. That means doublet. So what you are going to get is doublet and doublet. So overall the spectra of the molecule is going to look like two doublets. Okay, so the answer is going to be two doublets for this particular molecule. It was very simple. You just have to see the types of phosphorus and just find out the number of splitting based upon 2Ni plus 1 formula. Alright, let's go to the next question then. Okay, the next question which says the magnitude of bond angle. Okay, so how the magnitude of bond angle is going to change in the gaseous NF3, SBF3 and SbCl3. Alright, so to answer this particular question, there is a very simple concept which you should know about the bond angle, and it says that bond angle is actually directly proportional to electronegativity of central atom. Okay, and it's inversely proportional to electronegativity, inversely proportional to, so inversely we have to write down like 1 upon, so electronegativity of surrounding atoms. That means if the central atom has more electronegativity, the bond angle will be more, and if the surrounding atoms have more electronegativity, bond angle will be less. You have to go for this when the central atom is same. Okay, unless and until your central atom is same, unless and until you have different central atom, you have to stick to the first rule. So here you have three types of molecules. You have NF3, then you have SBF3, and you have SbCl3. Okay, that's what you have. Now if you look upon the electronegativity order for the central atom is nitrogen and antimony only. So if you look upon, so nitrogen electronegativity, okay, electronegativity, if I talk about electronegativity, so nitrogen has more electronegativity than the antimony, right? So that means what? The bond angle of your nitrogen containing compound, that means NF3 is going to be highest. Okay, so NF3 is going to be highest, so by that you can easily cancel out option number 2 and 3. Now looking upon the other factor where your central atom is same, now you have to look upon the electronegativity of subsidiary atoms. Okay, or the surrounding atoms. So in that particular case, the electronegativity order is like this, that fluorine has more electronegativity than chlorine, So if electronegativity is more, the bond angle will be less, right? So what you can say is that the highest bond angle will be for NF3. Then among here, fluorine has more electronegativity, right? So its bond angle, the antimony fluorine compound will have lower bond angle. All right, more electronegativity, less bond angle. It's like that. And chloride one will have higher bond angle. So it is going to be like SbCl3 will be more, and then you have SbF3. So in that particular case, your correct answer becomes your option number 4. You can understand it in this way also. If you want to understand in a more trivial way, just like you have been taught in your bachelor's or master's, is like when the central atom becomes more electronegative, electrons will be more concentrated towards its center. So if I show, see, the structures of all of these is going to be same. Okay, it's going to be trigonal, sorry, it's going to be pyramidal, right? The structure is going to be pyramidal according to your VSEPR theory. So that means nitrogen, and you have these three bonds which you can show them like this. Okay, so the three bonds can be shown like this. Now you have fluorine over here. So if the center, and you have antimony again, where you have, let's say, fluorides like this. So yeah, so if you have this, so if the central atom is more electronegative, electrons will be much closer to the central atom in these particular bonds, right? And if they are more closer to it, there will be electron repulsion in this, and that is going to make the bond angle higher. Okay, so these bond angles will become higher over here, and that's why they are going to be like the nitrogen compound is having more bond angle. So that's why NF3 is higher in that. Now talking about the one where you have fluoride and chloride, for that you can understand in this way, that if you have, let's say SbCl3 also we have. Okay, so what is going to happen in this particular case? So your electronegativity over here is more, so your electrons are going to be more near to your fluorine, right? So since electrons are away from the central metal atom, and here they are not going to be that much closer to chlorine, so more electron repulsion, one thing. The second thing is that due to bigger size of these chloride ions, there will be like interatomic repulsion, so that is going to cause more bond angle. So SbCl will have higher bond angle than Sf. Okay, so this is other explanation of the same thing, or it's much easier to understand it through this particular relation. You will never do this question wrong whenever it will be asked further in the exams. Okay, so the correct answer becomes your option number 4. Let's go to the next question then. Okay, the other question which says that the choose the correct statement for Oxy Myoglobin and cytochrome P450 resting state. Okay, both of them are in resting state from the following. Okay, there are 4 statements given to you. For that, this was actually asked from your bio-inorganic chemistry. Okay, and I always suggest you to keep on studying bio-inorganic chemistry, keep on reading the terms or topics from the bio-inorganic chemistry. If you have studied by Oxy Myoglobin and cytochrome P450, you could have answered this question very simply. Okay, it was very simple molecule, very simple question. So if you look upon the structure, basically, so for Oxy Myoglobin, you have iron and it's attached to porphyrin ring like this. Okay, so you have porphyrin ring to which it is actually being attached. Okay, so I'm not going to draw all the molecule, but yeah, this is how it is going to look like. Second also is going to have a central metal atom as iron only. Okay, and again the porphyrin ring is attached to this. So in both the cases, your central metal atom is actually attached to porphyrin ring. So both contains dianion of protoporphyrin. Okay, so option A is correct for both of them. Second says that both of them have fifth ligand bonded to the metal center from the protein backbone. Okay, now if you look upon and the same fifth ligand. Okay, so if you look upon the structure, there is a fifth ligand which is attached to both of them. For your oxymyoglobin, okay, this is oxymyoglobin, and this is cytochrome P450. So here, if you look upon for your oxymyoglobin, the fifth ligand or the fifth residue which is attached to this is your imidazole ring. Okay, you have imidazole ring which is being attached from the protein backbone. And for cytochrome P450, it is your cysteine. Okay, so it is cysteine basically. So this here you have imidazole, the nitrogen of your imidazole, and over here yeah, so this is imidazole residue, and this is cysteine residue. So that means what? They do not have same fifth ligand. So fifth ligand is not going to be same. So option B is wrong. Okay, now whichever option you have, where you have option B, you can just cancel out them. So you can just cancel out 1, 3 and 4. So by that, by default, you got answer number 2 as the correct one. You can check the other as well. The third statement says they contain single active sites. So yes, both of them contain single active sites. You should also know about, like, you can just differentiate between the molecules or the bioinorganic compounds which you have studied, which have single site, which have multiple sites, like that. So both of them have single iron site as the binding site. And the last D statement, which says they contain metal in +3 oxidation state. So yes, iron over here in Oxy Myoglobin is in +3 state, and here again iron in the cytochrome P450 is again in +3 oxidation state, in the resting state of that. So option number 2 becomes your correct choice. And one more thing, there you will also find in some books that oxymyoglobin have +2 oxidation state iron in it, but that's not like, see, it's very debatable thing. So in some books you will find it as +2, some books you will find it at +3. So it's not actually corrected everywhere. There are two theories. So one says that it's +2, one says that it's +3. So they will never going to ask you in a way that you are going to get stuck in between of that. Okay, just like the way they have given. So option D becomes obvious for you, so you don't have to think about it much. So it's having +3 oxidation state. You have to consider that for this particular question, right? All right, let's go to the next question then. Okay, in this question it says that the pair of lanthanide ion which shows significant deviation from experimental and calculated magnetic moment, considering contribution from the ground state only. So for this particular thing, I guess if you have watched my classes on Unacademy, the free classes which are already there, the videos, free videos which are already there, I have a course over there on lanthanides and actinides. There I have explained all the properties. Okay, they have just given all the exceptional cases, all the properties of lanthanides and actinides, and this question was directly from there. So if you know that, you could have answered this. So this is from the exceptional case of lanthanides. Okay, lanthanides. So you should know about this, that generally your samarium +3 should give a very low value of your magnetic moment. That should be 0.5 or something, and europium +3 should give you a 0 magnetic moment, but the observed one is quite high. It gives you around 1.9 or something, and it gives you around 0.9 or something. Okay, so you have a very higher value of so this is observed, sorry, this is expected. Okay, and this is observed. So these are the two ligands, or sorry, these are the two lanthanides for whom the observed values are very much higher than the expected values. So it was a very direct question from lanthanides and actinides, directly from the notes, directly from the question. So the correct answer is going to be your option number 4th. Okay, so 4th option is going to be the correct option. Alright, so that's all for this particular video, guys. I tried to take all the questions from the inorganic portion and try to explain you in the best form as possible from my side. So I hope you guys understood. If you guys have any doubt, you can ask that in the comment section below. One more important thing, that if you are new to this channel and if you like my content, do subscribe to the channel, give it a like, and share it with your friends. So thank you so much for watching, and see you guys in the next video.